In today's basic organic chemistry class, we'll be looking at the ethers. At the end of this class, you will understand how ethers are named, their method of preparation, their properties, reactions, and their uses. Ether compounds is a compound that oxygen is bonded by both sides with an alkyl or aryl group. In their properties, ethers are less polar than alcohols because they are very insoluble in water. They have low melting and boiling point than alcohols. Chemically, they are not reactive. That's why they are called inerts, and they are very flammable. In naming ether using common names, each carbon or each attachment is treated as a branch of oxygen. Remember, we have alkyl or aryl substituents that is connected by both sides of the oxygen. Then, when listing them, list each side with "-yl" ending. Then add ether at the end. This is still a popular method of naming. Common name is much more popular in naming the ethers. Example, when I have two methyl attached to both sides of oxygen, I call it dimethyl. That is 2-methyl ether. Ether that has 2 methyl. When I have methyl and ethyl, then when the substituents are not similar, the one that has the lower carbon comes first. The one that have the highest carbon becomes the one that connects the parent name, just like naming your name before your father's name. So that's why we have methyl ethyl ether. This last compound, we are naming chloromethyl because methyl is going to come first. But in that methyl, there's another substituent called chloro. So we call it chloromethyl ethyl ether. This is a common method of naming and still very popular way of naming ether. Employing IUPAC system. First, like any other nomenclature in IUPAC, you have to identify the longest carbon chain and use it as a base name. If the longest carbon chain is but, you call it as butane. One exception is if the shorter chain has a name altering functional group. So if the shorter chain is going to have a functional group, then you're going to consider it. Remember, functional group are given priority in IUPAC system of naming. Then name the shortest carbon chain with oxy ending, unlike the other one we're talking about naming with "-yl". Number location of ether bond. Wherever this ether bond is located on the chain, you have to give it the minimal number because it's a functional group of the compound. Then use other IUPAC rules of naming of substituents. Let's look at examples. This compound, if you look at the highlights, you realize that the smaller carbon is given a priority. So we have the carbon, naming it is going to give this substituent oxygen the minimal number. That's why we're going to start from the methyl substituent. We call it 1-methoxypropane. So we're naming it as an alkane with methoxy substituents. So the second one, we're calling it 1-chloro 1-methoxy ethane. Now, 1-chloro in the sense that the other carbon is having a substituent on carbon number 1, and we have to follow alphabetically. So we talk about 1-chloro 1-methoxy ethane. The next one, looking at this compound, the other one has 4. The one that is highlighted in blue has 3. So the one that has 3 is going to be given priority. Remember, looking at it, it's connected at carbon number 2 on the longest chain, the one of yellow. So we call it 2-propoxybutane. Butane is a parent name. The last one looks so confusing, but look at the functional group is alcohol. So we're going to name it as an alcohol. Then in that alcohol, we have a substituent on carbon number 3. And on that substituent of carbon number 3, it is called chloroethoxy. So that's what we call it. On carbon number 3, we have 2-chloroethoxy. Why is it 2-chloro? Because we're going to name it giving this oxygen priority. So the carbon that bears the oxygen is carbon number 1. Then the one that bears chloro is carbon number 2. So we call it 2-chloroethoxy. 1-butanol. We can also call it butanol. But we're trying to lay emphasis on where the hydroxy group is attached on the parent name. That's why we call it 1-butanol. We can also call it butan-1-ol. I hope that's clear. Generally, naming ethers, they are named by identifying the 2 organic substituents and by adding the word ether, which is the normal or common way of naming ether. If other functional groups are present, the ether part is considered as an alkoxy, just like we did in the IUPAC system, where we are talking about the substituents that have oxygen being oxy, methoxy. Now, this bond of ether is tetrahedral bond with bond angle of 112 in dimethyl ether. The oxygen in ether is sp3 hybridized. Oxygen atom gives ether a slight dipole moment. In this example, we have isopropyl methyl ether, ethylphenyl ether. Why is it ethylphenyl? Because ethyl is smaller, phenyl is bigger, so we call it ethylphenyl ether. Now look at the last one. We talk about para-dimethoxybenzene. They are in para position and there are 2, so we say 2-dimethoxy, 2-methoxy in para position in benzene ring. So that's what we call it, para-dimethoxybenzene. The last one is 4-tertiary butoxy 1-cyclohexane. The compound is 1-cyclohexane or cyclohexane. In that place, we have tertiary butoxy. That tertiary butoxy is connected to the cyclohexane at ring number 4. So that's why we call it tertiary butoxy, number 4 tertiary butoxy, 1-cyclohexane. So these are the means of naming ethers. We have some compounds that contain ethers. So ethers is not something that is isolated in nature, it's around us. In some drugs like vitamin E, you can see the ether functional group. Even morphine, which is an alkaloid, also contain ether. Ether is something that is also around us, is applicable around us, so it's not useless. Ether is being synthesized industrially by dehydration of ethanol or primary alcohols using sulfuric acid at 140 degrees. We call it limited dehydration, and it's going to follow SN2 pattern. SN2, bond cleavage and bond formation occur in a single step. But SN2 is concerted reaction, so everything happens at the same time. Under the same industrial synthesis of ether, in talking about diethyl ether, still the same thing we are talking about. They talk about 2 mole under sulfuric acid catalyzed at 140 degrees. We are forming our ether. Just all you need to know. The mechanism is not for your level. This method is not generally useful for synthesis of ether in the lab. Only symmetrical ethers can be made this way. Conditions are very compound specific. At 180 degrees, ethanol will yield ethane instead of ether. Remember, at 180 degrees, it's going to be complete dehydration to give ethane. So whenever you're talking about dehydration of ethanol, temperature will determine the product. 140 is ether, 170 and above is ethane. So the method employed in synthesis of ether in the lab is Williamson method of ether preparation. This involves reaction of metal oxide, primary alkyl halides, and tosylate. This is the best method for synthesis of ether. Oxides are prepared by reaction of alcohol with strong base such as sodium hydride. Looking at the reaction, cyclopentanol is an alcohol. Sodium hydride is a base. THF, tetrahydrofuran, is just a solvent. In the presence of primary alkyl halide, there is exchange of the sodium metal is going to go and form bonding with the halide, while the methyl is going to replace sodium. That's where we are going to have cyclopentyl-methyl. So this is the simplest and easiest way of preparing ether in the lab. So if the question comes, which of the following method is useful in synthesis of ether in the lab? Is Williamson synthesis, but in the industry is dehydration of alcohol. In Williamson synthesis, it is worthy of note that it's going to follow SN2 mechanism, where bond breaking and bond formation occurs in single step, and it can only occur using primary alkyl halide or methyl alkyl halide. The mechanism of this Williamson synthesis is SN2. In SN2, bond breaking and bond formation is occurring. So as the oxide is going to take the alkyl, the halogen, which is a good leaving group, will easily leave. Williamson synthesis can only occur with primary alkyl halide. When you have secondary or tertiary, it cannot be possible. So whenever talking about reactions of alkyl halide for Williamson synthesis, tertiary cannot do. It must be primary. This is not possible. Even secondary is not possible. The question is that, can this compound be made via the Williamson synthesis? Can this compound be prepared using Williamson synthesis? The question is no, because this is tertiary with ether. Williamson synthesis can only be synthesized using primary or methyl alkyl halide. The first method of preparation of ether in the lab is Williamson, and which is the best method. The second method is oxymercuration dematuration using alkane. So if you're in the exam and you're asked which of the following is not a method for preparation of ether, remember, whether industrial or in the lab, generally we have dehydration of ethanol, we have Williamson synthesis, we have oxymercuration and dematuration method. We can also use silver oxide catalyzed method to prepare ether. This is reaction of alcohol with alkyl halide. So silver dioxide is going to be the reagent or the system for this synthesis. So another method now is silver oxide catalyzed. So we have dehydration of alcohol, we have Williamson synthesis, we have alkoxy dematuration, we have silver oxide catalyzed for ether synthesis. Ethers are often used in the lab as solvents. They have low boiling points, which allow them to evaporate completely when used in reaction. Their dipole moment allows them to stabilize charged or partially charged transition states. And these ethers are not protic, so they are aprotic. Ethers are generally used as solvents in Grignard reaction. If you look at the table, we realize that ethers are not reactive. From this table, our own focus is on the blue highlighted for ether. So ether can react with acid, ether cannot react with bases. cannot react with metals. Ether cannot undergo oxidation, cannot undergo reduction, cannot react with halogens. So ether can only have one reaction, which is reacting with acids. In reactions, ethers are generally unreactive, but in the presence of strong acid, an ether bond can be cleaved. Example is ethyl phenyl ether. In the presence of hydrogen bromide, we are going to form a phenol because that alkyl part is being cleaved out and will form bromoethane. Epoxides. Epoxides are three-membered rings of ether which are called oxyrene. Industrially important as an intermediate. Is prepared using ethylene in the presence of oxygen and silver oxide catalyzed at elevated temperature to form epoxide, which is called ethylene oxide. Cyclic ethers behave like acyclic ethers except if the ring is three-membered. Example, dioxane and tetrahydrofuran. Remember, if you're doing a reaction, you see all this used as solvents, usually used as solvent in the lab. Tetrahydrofuran is what is written as THF whenever you're writing the equation of reaction. In preparation of epoxide using a peroxy acid, we can form an ether. Also, epoxides can also be prepared using peroxy acids. So epoxide is oxygen in a ring. Preparation of epoxide can also be done from halohydrine. Halohydrine is addition of HOX to alkene. So when this halohydrine is treated with a base, an epoxide is being formed. In the presence of water and dilute acid, 1,2-diol is always formed. So whenever you're talking about reactions of epoxide, what comes to your mind is if it's reacting with water and dilute acid, the product is going to be 1,2-diol. It means that I'm going to have hydroxy group as carbon 1 and 2, as seen in the equation. Halohydrines can also be obtained from epoxide. Remember, epoxide can be prepared from halohydrine. So halohydrine can also be formed from epoxide. From the reaction, when reacting epoxide with acid in the presence of ether as a solvent, we are going to form halohydrine. Remember, halohydrine is having hydroxy group and halogen in the same compound. So that's why we're going to use hydrogen halide in the presence of ether to form halohydrine. Greener reagent can also be added to epoxide. In that case, we are going to form alcohol. Remember in the slide of alcohol, how primary alcohol is prepared using greener reagent and epoxide. So that is what is happening here. So in the presence of this greener reagent, this epoxide, which is called ethylene oxide, the bond is going to cleave and we are going to form an alcohol. In the mechanism, when the bond between the carbon and oxygen breaks, oxygen is going to be electronegative, carbon will be electropositive. And when the bond between magnesium and carbon breaks, magnesium is highly electropositive, while carbon is going to be electronegative. So that the negative aspect of carbon is going to bond to the positive aspect of carbon, while the magnesium that is electropositive will go and bond with oxygen. Under acid hydrolysis, this bond of magnesium is going to cleave out. So we're going to have alcohol. That is why with greener reagents, our ethylene oxide or epoxide can form alcohol, primary alcohol precisely. A cyclic, another larger ring, cannot react. This reaction can only occur with ethylene oxide. Large rings that have repeated ethoxy or similar units are called crown ethers. How are they named? Named as X crown Y X is the total number of oxygen atoms in the ring, while Y is the total number of oxygen atoms. So if I have 18 crown 8 ether, it means I have the 18 is the total number of atoms in the ring, while 6 is total number of oxygen in the ring. So that is how ethers are named. They are named by total number of atoms and total number of oxygen. So the atoms is a crown, the oxygen is the ether. So 18 crown 6 ether means 18 atoms 6 oxygen. Means that the ring contains 18 carbons, while the oxygen in the ring is 6. Crown ethers have been shown to form especially strong attraction with metal atoms. If you look at the compound, you can realize that we have 12 crown and 4, meaning the carbons is 12, while 4 is oxygen. The other one will have 15 crown and 5. The 5 is oxygen. So the number of carbon and number of oxygen. So note how many carbon atoms separate the oxygen. We've come to the end of this class. In summary of ethers, what you need to know as a student of 213, talk about are ethers reactive, they are non-polar, they are very flammable, their best method of synthesis is Williamson. Ether can also be other methods are being used. Industrial method of preparation of ether is also important. Temperature of 140 degrees, 2 mole of alcohol. Then understand what are crown ethers. Understand that oxide or ethylene oxide can be used in preparation of primary alcohols. These are the things you need to note concerning ether, wishing you success in your 213 exams.